So one of my viewers posed a very interesting question. Thank you to them. In that, why does the series representation of the natural log have a range requirement on x? Well, let's get down to the fundamentals. A elementary function, or any elementary function, can be represented as a polynomial, right? What's the best way of writing a polynomial? Well, or not the best, there is no best way. The most general form of writing a polynomial is something like this, right? A n x to the n from n equals 2 infinity. I mean, n equals 0, n equals 1, it is what it is. It doesn't matter, but you get the point, right? It's an arbitrary coefficient, a to the n, it could be anything, times x to a sequentially increasing power. There is actually a connection between this and the linear combination of independent basis vectors in vectors, but that's something else. I'll talk about that another time if you want. But this series will only ever converge to a function if x is less than a value called the radius of convergence. So we can see here that 1 is the radius of convergence for this function, but why is that? And what does it mean to be a radius of convergence? Well, it kind of really is what it says on the tin, right? It's a length for which x must be within for the series to converge. Looking at it in this form is not really very intuitive. There's nothing I can really draw from this, and there are expressions to derive it, but that's quite a bit more than A level, which is what this topic is within. So I'll try to explain it intuitively with this. So when x to the n increases with n, it obviously gets much bigger, right? And it gets pulled back down by this 1 over n, right? And that's why you see the function for the natural log, it doesn't blast off into infinity, it stays quite low, because these two kind of cancel each other out. But when x is greater than the radius of convergence, this 1 over n, it fails to pull it back down, it grows up so high, and the series diverges off into infinity. That's why x must be less than the radius of convergence. But how can we work that out? Well, it's actually quite simple in the case of a Maclaurin series, we can take the point of expansion 0 and subtract it from the first singularity point, which we can see here is going to be x equals minus 1, because when we have ln of 1 plus minus 1, we get ln of 0, which is a singularity. That's a first singularity. So that gives us a radius of convergence of 1, which is exactly what we want there, right? It makes sense, right? But then you may be asking where this comes from. Well, if x is negative 1, that's infinity, so we can't evaluate the series in that case. And if it's 1, then it's the radius of convergence, we can't evaluate in this case. So for the best approximation of this series, x must lie between negative 1 and 1. So yeah, that's a general explanation for the radius of convergence. And in fact, you can consider that for any series, but the thing is, for something like sine or cosine, if I just rub this out, because you did ask how to work it out for other series. Well, it's what I said. You start at the start point for the expansion 0 in most cases and go to the first singularity. But for something like cosine into the n x factorial, this doesn't have a singularity. So the radius of convergence is infinite. So as long as x is less than infinity, this series will converge. And the same goes for most functions. In fact, in A level, I think this is the only one that we see that has a singularity. Oh no, tan as well. Tan has a singularity at pi over 2, I think it is. So the radius of convergence there will be pi over 2. But I think there might be a bit more nuance to that. But I think that's a general aspect you can think about it. So, for example, the tan series is only valid for x less than pi over 2, I think. But that also might be wrong as well, because it's a periodic function, so you might need to consider Fourier series, which is outside the A-level spec. But if you want me to cover that, I can. But interestingly, that series that I wrote before, a to the n, x to the n, this has a very interesting connection to vectors. You know how vectors can be represented as a linear combination of basis vectors. Like the vector 1, 1, 1 is just a combination of each unit vector. This can be thought of in the same way, and we consider that a lot when you go further in maths and physics. So if you want to have a look at that, or if you want to learn more about that, I can make a video about that in the future. But yeah, I hope I answered your query decently, and yeah, thank you.